Introducing Docker containers. Containers have become popular due to the rise of Docker as a container virtualization platform. This lightweight platform provides tooling to create, store, manage, and run containers. It is easy to integrate with automated build, test, and deployment pipelines. Docker offers several important benefits. First, it is a portable runtime application environment. You can package an application and its dependencies into a single immutable artifact called an image. After you create a container image, it can go anywhere Docker is supported. You can run different application versions with different dependencies simultaneously. These benefits lead to faster development and deployment cycles, and better resource utilization and efficiency. All of these abilities are related to agility. Docker containers are created from read-only templates, which are called container images. Images are composed of layers and are immutable and highly portable. You can port an image to any environment that supports Docker. Images are built from a Docker file, which is a plain text file that specifies all of the components included in the container. Instructions in the Docker file create layers in the container image. You can create images from scratch, or you can use images that others created and published to a public or private container registry. An image is usually based on another image with some customization. For example, you might build an image that's based on the Ubuntu Linux image in the registry. The image could also install a web server and your application in addition to the essential configuration details to make your application run. A container is a runnable instance of an image. You can create one container or several containers based on that image. Each container has a thin read-write layer on top of the existing image when it is instantiated. This architecture is what makes the actual process of instantiating the containers fast. Most of the actual work is read-only because of the file system layers. The read-write layer of the container enables your application to function properly while they are running, but it's not designed for long-term data storage. Persistent data should be stored in a volume somewhere. Consider a container as a discrete compute unit, not a storage unit. To build your own image, you create a Docker file using a simple syntax to define how to create and run the image. Each instruction in a Docker file creates a read-only layer in the image. In this simple example, you start with the Ubuntu latest image, which is already created for you and hosted on Docker Hub or some other site. The only thing you do is add a command to echo the message "Hello World" after the container is instantiated. This is a slightly more involved example in which you want to run a Java application. You start with the Open Java Development Kit, or JDK, version 8 image. You copy the .jar file containing your code from your system to the container, and then call Java to run your code. When this container is instantiated, it runs the Java application. This is a more real-world example of a Docker file. You start with a CentOS 7 image. Next, you update the OS and install Apache. Then you expose port 80. Finally, you copy the shell script for your application and give it run permissions. After the container is instantiated, the command will run the shell script. This example shows how the code from the previous example looks in terms of layers. Each instruction in the Docker file creates a layer. The first layer, starting from the bottom of the diagram, is the base layer. The next layer includes the software update and the Apache installation. The next layer opens and exposes port 80. The layer after that includes the command to copy the shell script. Finally, the last layer makes the shell script run. These layers are all read-only, which makes the container image an immutable object. If you change the Docker file and rebuild the image, only the layers that have changed are rebuilt. This feature is part of what makes container images so lightweight, small, and fast compared to other virtualization technologies. Thanks for watching, and see you in the next video. Section 3, Part 2, Introducing Docker Containers. You can run Docker Command Line Interface, or CLI, commands from a Bash terminal to manage your Docker images and containers. For example, you can build an image from a Docker file by running docker build. Verify your image by running docker images. To launch a container from the image, run docker run. To verify the container is running, enter docker ps. After launching a container, you can interact with it in a variety of ways. To open a bash prompt on your running container, use docker exec. You can also stop a running container and start it again by using docker stop and docker start. To view your container logs, enter docker logs. To list the port mappings for your container, run docker port. Run docker tag to tag your image, and use docker push to push it to a registry. This example runs the docker build command to create an image from a Docker file in the current directory. The tag option names the new image node_app. The actual output would show the progress of each instruction in the Docker file, steps 1 through 7. This example runs the docker images command to list the images that your Docker client's aware of. The actual output might include other images, but the example output highlights the image that was created with the build command in the previous slide. The actual output would show the progress of each instruction in the Docker file. This example runs the docker run command to create a container from the node_app image. The -d or -detach argument specifies that it should run in the background and print the container ID. The -name argument specifies that the container should be named node_app_1. The -p or -publish argument specifies to publish container port 8000 to the host port 80. By default, when you create or run a container using docker create or docker run, it does not publish any of its ports to the outside world. The -p tag makes a port available to services outside Docker or to Docker containers that are not connected to the container's network. This technique creates a firewall rule, which maps a container port to a port on the Docker host to the outside world. The visible output of this command is the container ID. You could follow this up with the docker ps command, as illustrated in this slide, to further verify that the container is running. This example uses the docker exec command to open a terminal window on the running container. In this way, you can interact with the contents of the container. When you run docker exec with -it container name sh, Docker attempts to open an interactive connection to the shell running on the container. The -t specifies that you want a terminal session to be invoked. The -i specifies interactivity so that the terminal session you invoke will stay open. You can continue to run commands and interact with the contents of the container until you exit the terminal. In this simple example, after connecting to the container and opening the terminal session, ls is used to list the contents and then exit to end the session. This example runs the docker stop and docker rm commands to stop and then remove the container named node_app_1. The visible output of this command is the name of the container for each part of the command. Stop and remove. You could again follow this up with the docker container ls command to further verify that the container has been removed. Here are the key takeaways for this section of the module. Docker containers are created from read-only templates, which are called images. Images are built from a Docker file and often based on other images. Containers are runnable instances of an image with a writable layer. A container registry is a repository of images. And to manage your Docker images and containers, you can run Docker CLI commands from a Bash terminal. Thanks for watching, and see you in the next video. 5 Part 1. Introducing AWS Container Services. Recall the shipping container analogy. Suppose you have one ship and a half dozen containers. Keeping track of what's being shipped on which transport, the schedule of starts and stops, and the state of the containers is manageable. However, what happens when you scale up the number and type of transportation methods and the number of containers? Scheduling and managing which are loaded, where, and when requires a lot more logistical effort. Likewise, with running software containers, running 1 or 2 containers on a single host is simple. But things get complex when you move into environments with tens of hosts and possibly hundreds of containers, or a full production environment with hundreds of hosts and maybe thousands of containers. You now must manage an enterprise-scale clustered environment. You must know the state of everything in your system. For example, you need to know which containers aren't working and which are starting and stopping. You need to know where you have enough room and memory to add new containers. Finally, you must place your containers intelligently on instances to maximize availability, resilience, and performance. Container orchestration platforms become useful here. They handle scheduling and placement of containers based on the underlying hardware infrastructure and application needs. Such platforms integrate with other services, such as services for networking, persistent storage, security monitoring, and logging. Many options exist, including native tools like Docker Swarm, open source platforms like Kubernetes, and the Amazon Elastic Container Service, also called Amazon ECS. Amazon ECS is a highly scalable, highly performing container orchestration service that supports Docker containers. It scales rapidly to thousands of containers with no additional complexity, schedules placement across managed clusters, and integrates with third-party schedulers and other AWS services. Amazon Elastic Container Registry, known as Amazon ECR, is a fully managed container registry you can use to easily store, run, and manage container images for applications that run on Amazon ECS. It is scalable and highly available, integrated with ECS and Docker CLI, and secure. This includes encryption at rest and integration with the AWS Identity and Access Management Service, also called IAM. This slide shows a high-level overview of Amazon ECS. First, container images are pulled from a registry. This could be Amazon ECR or a third-party or private registry. Next, you define your application. Customize the images with the necessary code and resources, and then create the appropriate configuration files. Then, define your containers as short-running tasks or long-running services within ECS. To bring your services online, you select one of 2 launch types, AWS Fargate or Amazon Elastic Compute Cloud, or Amazon EC2. You can mix and match the 2 types as needed. Finally, you can use Amazon ECS to manage your containers. ECS scales your application and manages your containers for availability. The Fargate launch type provides a near serverless experience where AWS manages the infrastructure supporting your containers. AWS manages placement of your tasks on instances and makes sure each task has the appropriate amount of CPU and memory. With Fargate, you can focus on the tasks and application architecture instead of worrying about the infrastructure. Choose Fargate when services are subject to wide swings in demand. You have large workloads optimized for low overhead, you have small test environments, or you have batch workloads that run on a schedule. The Amazon EC2 launch type is useful when you want more control over the infrastructure. With this launch type, you create and manage clusters of EC2 instances to support your containers. You also define container placement across your cluster based on your resource needs, isolation policies, and availability requirements. You have more granular control over your environment without operating your own cluster management and configuration management systems or worrying about scaling your environment infrastructure. Choose EC2 when your resource requirements are more predictable, or you can use reserved instances to reduce costs. You have large workloads optimized for price. You need to comply with organizational security requirements. Or you have excess EC2 capacity. That's it for this video. Thanks for watching, and see you in the next video. Section 5, Part 2, Introducing AWS Container Services. You can programmatically access Amazon ECR from the AWS Command Line Interface, or AWS CLI, and by using the APIs. You can use the AWS CLI and APIs to create, monitor, and delete repositories and set repository permissions. You can perform these actions in the Amazon ECR console, which you can access from the Amazon ECS console. Amazon ECR integrates with the Docker CLI, which allows you to push, pull, and tag images on your development machine. This example shows how to create a repository called Hello World with ECR. The example uses Docker CLI commands to build and tag an image, and then push it into the repository. To push an image into the ECR, you must first authenticate the Docker client to your ECR registry. Kubernetes is an open source container management platform you can use to deploy and manage containerized applications at scale. Kubernetes manages clusters of EC2 instances and runs containers on those instances with processes for deployment, maintenance, and scaling. By using Kubernetes, you can run any type of containerized application by using the same tool set on-premises and in the cloud. You can use AWS services to run Kubernetes in the cloud. Amazon Elastic Kubernetes service, called Amazon EKS, is a managed service that runs the Kubernetes management infrastructure across multiple availability zones to reduce the chance of a single point of failure. EKS is certified Kubernetes conformant, so you can use existing tools and plugins from partners and the Kubernetes community. Applications that run on any standard Kubernetes environment are fully compatible and can be migrated to EKS. Amazon EKS automatically sets up secure and encrypted channels to your worker nodes, which makes your infrastructure running on EKS secure by default. AWS actively works with the Kubernetes community, which helps EKS users employ AWS services and features. When you select Amazon EKS as your container management service, you provision an EKS cluster and deploy Amazon EC2 or Fargate worker nodes, worker machines, for your EKS cluster. Then you connect to EKS and run your Kubernetes applications. Here are the key takeaways for this section of the module. Container orchestration services, or systems, simplify managing containers at scale. Amazon ECS is a fully managed container orchestration service that you can use to launch containers to either Fargate or EC2 instances. Amazon ECR is a fully managed container registry service. And Amazon EKS is a managed service that you can use to run Kubernetes in the cloud. That's it for this video. Thanks for watching, and see you in the next video. Let's review the module and wrap up with a practice certification exam question. In summary, in this module, you learned how to describe the history, technology, and terminology behind containers, differentiate containers from bare metal servers and VMs, illustrate the components of Docker and how they interact, and identify the characteristics of a microservices architecture. You also learned how to recognize the drivers for using container orchestration services and the AWS services that you can use for container management, host a dynamic website by using Docker containers, and describe how Elastic Beanstalk is used to deploy containers. Now, let's take a look at a sample exam question. A cloud architect wants to migrate a web application to containers. The team does not have much experience with AWS or containers, but the architect wants to get them started quickly to be able to experiment. Which solution would be best? A, use Elastic Beanstalk to launch a multi-container Docker environment. B, use Amazon ECR to host Docker images that they create from scratch. C, configure EC2 instances with automatic scaling and install Docker images on the instances. D, configure Amazon ECS with a cluster of EC2 instances that run Docker containers. Note the key requirements stated in the problem. The solution needs to take into account that the team doesn't have much experience with AWS or containers, but the cloud architect wants to get them started quickly to be able to experiment. Consider the answer choices and rule them out based on these key requirements. We'll pause a few seconds before discussing the correct answer. If you need more time to consider the answer choices, pause the video. So how do these answer choices compare to the requirements? First is using Elastic Beanstalk to launch a multi-container Docker environment. That could be the answer. Second is using ECR to host Docker images that they create from scratch. To get started quickly, the team wouldn't want to create images from scratch. Therefore, this doesn't seem like the best option. Next is configure EC2 instances with automatic scaling and install Docker images on the instances. This would require AWS and container experience, and it's time-consuming. This wouldn't meet the requirement for a team without a lot of experience who wants to get started quickly. Finally, configure ECS with a cluster of EC2 instances that run Docker containers. This would not meet the requirements because Elastic Beanstalk uses ECS to coordinate container deployments to multi-container Docker environments. This coordination simplifies the task of getting up and running with containers. Elastic Beanstalk takes care of Amazon ECS tasks, including cluster creation, task definition, and running tasks. The correct answer is A. You can use Elastic Beanstalk to set up a working multi-container Docker environment. You don't need to deal with the details of configuring instances, networking, and IAM permissions. You might want to use Amazon ECR, but you would want the team to use existing images as a starting point. That concludes this module. Thanks for watching, and see you in the next video.
Welcome to Module 9, Caching Information for Scalability. We'll begin with Section 1, Introduction. At the end of this module, you should be able to explain when caching is used, describe caching with Amazon Elasticache and Amazon CloudFront, describe and compare Lambda at Edge and CloudFront functions, and apply caching strategies. This module includes an overview of caching and information about caching with Elasticache, caching with CloudFront, and caching strategies. The cafe employees have gotten occasional customer feedback that the coffee bean inventory information takes too long to display on the cafe website. Sophia wants to reduce the latency and also update the site to support HTTPS traffic. Olivia, the AWS consultant, proposed adding database caching to improve the speed of returning the coffee bean inventory information. Sophia wants to set up a content delivery network, or CDN, to ensure the site loads as quickly as possible and to support HTTPS. This diagram gives an overview of the application you will build through the labs in this course. The highlighted portions are relevant to this module. As highlighted in the diagram, in the first lab, you add database caching using Amazon Elasticache for Memcached. In the second lab, you configure an Amazon CloudFront distribution to reduce network latency and deliver website content securely over HTTPS. That's it for this video. Thanks for watching, and we'll see you in the next one. Covers Section 5, Caching Strategies. Caching has two primary strategies, lazy loading and write-through. The lazy loading strategy updates the cache only when necessary, as in a cache hit or a cache miss scenario. Use lazy loading when you have data that will be read often, but written infrequently. For example, in a typical web or mobile application, a person might update their profile only a few times per year. However, the profile might be accessed throughout the application dozens or hundreds of times a day, depending on the user. The write-through strategy adds data or updates data in the cache whenever data is written to the database. Use a write-through caching strategy when you have data that must be updated in real time. Think of this strategy as being proactive. You can avoid unnecessary cache misses when you have data you know will be accessed. A good use case for this strategy is any type of aggregate, such as a top 100 game leaderboard, the top 10 most popular news stories, or even recommendations. Because a specific piece of application or background job code typically updates this data, it's straightforward to update the cache also. With lazy loading, only requested data is cached. An advantage is that lazy loading avoids filling up the cache with data that isn't requested. Additionally, node failures are not fatal. When a node fails, a new empty node replaces it. The application continues to function, though with increased latency. As requests are made to the new node, each cache miss results in querying the database and adding the data copy to the cache. Subsequent requests for this data are retrieved from the cache. The disadvantages include the cache miss penalty discussed earlier and the potential to get stale data. If data is written to the cache only for a cache miss, then the cache isn't updated when data is changed in the database. Therefore, data in the cache can become stale. This example shows the lazy loading workflow in Python pseudocode. With write-through, when you update the database, you update the cache. The advantage is that cache data is never stale because the data is updated every time it's written to the database. However, this approach has a few disadvantages. First is the write penalty. Every write involves two trips, a write to the cache and a write to the database, which adds latency to the process. Still, users are generally more tolerant of latency when data is updated than when data is retrieved. Users have a general idea that updates are more work and thus might take longer. The second disadvantage is missing data. When a new node is created to scale up or replace a failed node, the node does not contain all of the data. Data continues to be missing until it is added or updated in the database. In this scenario, you might use a lazy loading approach to repopulate the cache. Another disadvantage is unused data. Because most data is never read, the cluster could have a large quantity of data that's never read. Finally, cache churn. This is when the cache might be updated often if certain records are updated repeatedly. This example shows the write-through workflow in Python pseudocode. Here are the key takeaways for this section of the module. Caching has two primary strategies, lazy loading and write-through. With lazy loading, the cache is updated only when necessary for a cache hit or miss. With write-through, the cache is updated whenever data is written to the database. Choose a caching strategy that matches the use case for your data. That's it for this video. Thanks for watching and see you in the next video.